Welcome back. Today we're going to talk about radioactivity. So you of course have heard of radiation and radioactive materials. So today we're going to talk about that. Exactly that. We'll go into details, but we'll discuss what is an atom and what is a nucleus. What are the ionizing and non-ionizing radiations? What is that? And the uses of radiation. Let's get started. Radioactivity. The official definition of radioactivity is the random and spontaneous decay process of an unstable nucleus. So what do you define random? Random is the probability of happening is the same. So let's say a nucleus has the probability, let's say there's two nucleus. They both have the same probability to decay. Spontaneous is they decay in concurrent with time. Which means they decay whenever they want. There's no time limit, there's no time frame. They just decay, right? That's spontaneous. So radioactive radiation consists of three things: the alpha particles, the beta particles, and the gamma rays. So go into these into details, right? So radiation, there's all three types of radiation. There's gamma rays, beta particles, sorry, and alpha particles. As you can see through the names, both alpha and beta are particles, while gamma are rays. Keep this in mind. This is very, very important in the future. So what do you use to measure radioactivity? Well, you just say use a tool, right? So what unit is that tool based on? So one of the units is Curie, which is how many decays per second, right? And the other one, which is the official unit, is Becquerel, which is 1 decay per second. So there is how many decays per second, right? So 1 becquerel is 1 decay per second, while 1 curie is 3.7 times 10 to the power of 10 decays per second. So curie, let's just draw, since I highlighted. So curie, right? Curie is the bigger one, the larger one. This one is more easier. So I'll say, oh, there's the radioactivity of this is 3 curies. So for the number of barocule is going to be much more larger because it's 1 decay per second, right? Wait, sorry. 1 decay per second. So to know about radioactivity, you need to first know about half-life. So what is half-life? Half-life is the time taken for a nuclei to reduce or decay to half of its original number. So let's say this is a uranium-283 particle, yes? This is a uranium-283. So it decays to half, which means it decayed to half its weight, right? This is uranium-283. It decays to half its weight and it decays half more. So one of these is a half-life, right? So that's the meaning of half-life. It means the particle decays, this thing decays to half. So this thing is gone. Half of this is gone, right? So the time taken for it to remove half of the atom or the nuclei is called half-life of radioactive decay. So as you can see, the first half-life, you can see measured here from 0 to 5 days, it decayed to half. So the half-life of this radioactive material is 5 days. Calculations of half-life. Oh, that's an editing error. We have 2 arrows there. Anyways, so you calculate half-life by using the graph. You see the graph, the activity by Berkel, and time. So this one is t, right? This one is time taken by seconds. So as you can see, the original activity is 800 barocles, and then it reduced to half of its activity, which is 400. So this is a half-life, right? So 400, you use a graph to find 40 seconds. Meanwhile, when it's 400, its half-life is when it reduced to half, which is reducing to 20. So you see the half-life, the second half-life is 80 seconds. That's why the graph slope is, the gradient of the slope is declining. Because as you can see, and you get smaller and smaller and smaller, the ratio is still half. while it needs to have the same time for it to decay. So it decays slower in relevance to time. So the original activity is 800 barrecoules. The half-life activity is half of 800, which is 400 barrecoules. So by referring to the graph, you can find the half-life is 40 seconds. So now we get into the nitty and gritty chemical stuff, right? So you need to know radioactivity, you need to know about an atom. So what is an atom? So the structure of the atom looks similarly like this. There's two types of stuff in the middle, which makes up the nucleus, which is a nuclei, and there's things revolving around it, right? So what are the things revolving around it? Those are the electrons. The electrons are negatively charged particles. Meanwhile, the things inside the nucleus consist of one, positively charged particles, which is called protons, and the other yellow color ones are neutrons, which neutral particles, it comes with a name. So electrons is negatively charged, protons are positively charged, and neutral particles are neutrons, which has no charge. So how do you form positive and negative ions? So here you need to differentiate between an ion and an atom. An ion has charge. An atom or a molecule doesn't. It's balanced. The number of electrons and the number of protons is the same, although the number of neutrons might be different. That one is another case, but just know that the charge of the atom is dependent on the number of electrons balancing out with the number of protons. However, if say you remove one electron or you add one electron, so that means you disrupt the charge of the atom, so it turns into an ion. So a cation and anions are the two different types of ions. Cations are neutral atoms that loses electrons, so they are positively charged, because now when you lose one electron, say you have six protons and six electrons. Yes, six electrons. So now your electrons only have five, but you have six protons, right? So now you have an imbalance of charges, because you have six positive charges but only five negative charges, because one of the electrons are removed. So now the entire atom turns into positively charged atoms, because now there's more positive charge, so it turns into a cation. Similarly, in an anion, the neutral atoms gain electrons, so they receive electrons. Now 6, 6, it turns into 6, 7. So now electrons are more than protons. So now it's more negatively charged. Now it's not balanced anymore, right? So now we'll get into the more main topic of this subject, of this chapter, right? So it's the ionizing and non-ionizing radiations. You might be wondering, what the heck is an ionizing radiation? So, well, when radiation moves through the air, ionizing radiation produces anion and cations. So they ionize the air particles to form protons and to form different charged atoms, right? So non-ionizing, so the spectrum of ionizing and non-ionizing reaction is as follows. So as you can see, anything before light, although they are a type of radiation, say your radio wave, your microwave, your infrared rays. Infrared rays, if you don't know, is the stuff where it helps you see heat. So you know how night vision goggles? Yeah, they're infrared, right? Very low frequency waves. This one is not in your syllabus, but yeah. Then visible light. This is the endpoint, right? These are types of non-ionizing radiation, where they do not disrupt the balance of the charges in the air. Meanwhile, anything after this, you might have heard that X-rays are not good for you. Ultraviolet rays, UV rays, whatever, is not good for you, right? Gamma rays obviously is not good for you. So these are ionizing radiations, which in turn it makes the environment where the radiation happens charged, and that's not good for our health. We'll get to that in a minute. So there are actually two types of ionizing radiation. There's actually quite a lot actually, but what you need to know is there's three types of ionizing radiation, right? It involves the alpha particle, the beta particle, and the gamma particle. So I'll let you guys envision this, right? You imagine a basketball. That's an alpha particle, right? Beta particle are, say, a pea. Compared to the basketball, the pea is so much smaller. And I'm talking about the vegetable, yeah. The pea is one singular like pea is so much smaller than a basketball, yes. And then gamma rays are basically just you point a laser, right? This ray is a light ray. It's like a ray. It's like a light ray that doesn't have particles, right? So now alpha radiation are positively charged. They are massive. They're huge, right? They are positively charged. Beta radiations are negatively charged because they are mostly consisting of electrons. And the gamma rays, which is the EM wave, electromagnetic wave, they have no charge because, well, they don't have particles. They're just a ray, right? So the ionizing power depends on the size of the particles. So now alpha radiation has a huge size. So because it is positively charged and it is big, right? It is big. So now it can attract the negative, the electrons away from, let's say, the air more easily to ionize the surroundings because it's huge. Meanwhile, beta radiations, they are small because they are electrons. They're negatively charged, so they will cause an imbalance as well. But the magnitude is moderate, it's only quite low, right? Actually, it's quite low. But compared to gamma rays, which has no charge, they have very, very low ionizing power. So even though, say, the light spectrum is a type of EM wave, but it's not harmful to our body, right? So and then after ionizing power, we discuss the penetration power of the radiation. And you need to remember, alpha is big, huge, right? Betas are small. So what happens is when you put, say if you put a fence, right? A little hole, like moderate holes, like a normal fence, right? You throw a basketball, it's not gonna cross. You throw a pea, it's gonna cross, right? Because the pea is also damn small. And then if you shine a light, it's definitely gonna cross. It doesn't matter if it is like a filter paper or whatever, it's still gonna cross because it's a light ray. That's exactly how you should think about it in this circumstance. So the penetration power of alpha radiation is low because they're huge. They are hard to penetrate. Beta radiations have moderate penetration because although they are quite penetrative compared to gamma rays, they still can't really penetrate a lot of the surfaces, right? But gamma rays, oh, they're light rays. They can easily penetrate anything they want, right? And then the deflection by charged plates. So what is this? Basically, you shine like a beam of alpha beta particles. You put like positive and negative plates, right? So you need to understand, being a big particle, it's heavy. Being a small particle, is light. So if they're negatively charged, they're gonna be attracted to the positive plate because, well, negative positive, the different charges attract, right? It's like the north and south pole. So for the alpha radiation, you see something like this. This is a negative plate. This is a positive plate. You see something like this. Yeah, it's quite. There's a deflection, yes, because, well, they are positively charged. They're going to be attracted to the negative part. Deflection is quite slow though, right? Well, for the second circumstance, you see for the beta radiation is something like this. This is a big deflection. You know why? Because they're light. They're electrons. They're light. So the beam is easily diverted, right? Because the alpha radiations are huge. And then for gamma rays, because they have no charge, no attractions happens because they have no charge. They don't give a shit. Yeah, I shouldn't curse on here. Okay, they don't care, right? They don't care, and then they just move through because they're not attracted by either poles. And this one is okay. There's an actual physics law for this, but you'll not learn right now. So for the meantime, uh, you don't need to memorize. You just need to know this exists because this one will help you in the future. All right. So now we have looked into what is an ionizing radiation and what types of ionizing radiation we have. we now look into the sources of ionizing radiation. So there are two sources basically. One is natural and one is man-made. So the natural ionizing radiation are the cosmic rays, which is the rays in outer space, and some sort of radiation in the background called background radiation. Everything they everything we use have radiation, right? So man-made radiation, ionizing radiation is like you use radioisotopes, which is basically unstable nucleus to prompt radiation to happen, like those like uranium 238 283. It's used in nuclear power plants, so to initiate like the scientists already know that that nuclei is not stable, so it's called a radioisotope because they pumped more neutrons into it. That's an isotope, but that's not in the syllabus. So they essentially make it not stable synthetically to prompt it to release radiation so they can use it for the nuclear power plants. And the other one is nuclear accidents, of course, and nuclear tests. So anything man-made is like, yeah, the bomb as well. So cosmic rays. Cosmic rays are high energy radiation produced outside the solar system. Basically comets and stuff like that. Sometimes you see streaks in the sky at night, right? So those are cosmic rays. So they're galactic cosmic rays. They're also called galactic cosmic rays. So background radiation are various types of ionizing radiation in the background. So it can be natural or man-made, like cosmic rays can be counted as background radiation. It's like this big category that envelopes everything, right? So now, how do we measure background radiation? It's important because, well, since radiation is in our everyday life, you need to know if it has significant health, like, does it endanger our health, you know? So how do we measure it? As you say, the biological effect is measured in dose. So one unit of dose, the unit of dose is 1 microsievert per hour. You just need to remember the unit. So the safe dose of ionizing radiation for us humans is less than 0.2%, 0.2 microsievert per hour. And well, anything other than that, you will be in danger of, radiation side effects or the effects of radiation. So the safety measures to minimize exposure to ionizing radiation is one. There's actually probably one is we just use protective equipment such as anti-UV rays for umbrellas or our glasses. Like I'm wearing a glass. I'm wearing glasses right now. It has UV protection glass planes, so it protects me from the UV radiation. When taking an X-ray, you follow the doctor's instruction. Don't simply go and take an X-ray and just burn through your body cells. 3, don't stick your eyes in front of the television. Like don't be too close to the television. Like I know this is a big cliche of how like your parents or your grandparents used to say to you, but like television emits radiation. Let's be honest, right? So you being too close, you gonna expose yourself to the downside of it. It's gonna be too much for your body to handle. So, and fourth, general knowledge, like it's common sense, you don't eat food that has been contaminated by radioactive substances. Like, for instance, if there's any nuclear spills in nuclear power plants, yeah, just avoid any fishes from the area, yeah, or any like of the land crops or anything. So say right now uh, say right now I'm Malaysia, right? We don't really have any nuclear power plants. So if we do have a nuclear power plant and it's exploded and nuclear leaks, right? So well, just don't eat food from Malaysia, I guess, until well it gets clean and clear and tested that the radioactivity is decreased, and then even after that, you need to you need to consider, yeah, you need to consider. And the last one is cosmic rays. So cosmic rays, you can actually get exposed in Earth. It's just not it's not only in outer space, so you can actually see it from Earth. So the people with the most risk exposed to cosmic rays is actually pilots because they fly so close to the stratosphere, which is the third layer of the Earth atmosphere, if I'm not mistaken. And yeah, so the working hour of pilots are actually limited. All right, I think I met a pilot once. It's like they have a rule of saying you can only fly 600 hours per year. 600 hours in the air per year, right? Per pilot. Long haul pilots is 500. So they decrease for long haul because you're exposed for longer, right? So that's how they reduce and minimize exposure to ionizing radiations for pilots especially. The uses of radioactive radiation include 1. Archaeology. So the method used in archaeology today is called carbon-14 dating. You might wonder, because you might remember from the periodic table, well, carbon's 12, right? Yeah, carbon's 12. But you add 2 more neutrons into it, it becomes an isotope, it becomes unstable. So it becomes a radioactive substance. Carbon-14 dating is basically, we measure the activity of C14. It has a half-life of 5,000 years, right? Carbon-14 is actually around us. It is an isotope that's present in nature, but the percentage of it is quite low. So carbon-12 is like 96%. Carbon-14 is about 1.2, and then the others are like carbon-13, like that, right? So by measuring the activity of carbon-14 in, say, a dinosaur, like how much carbon-14 is left, or the carbon-14 is left, how much of the carbon-14 is left, right? I would say, let's say we can't really like measure one atom of carbon-14, but let's say we can measure one atom of carbon-14. So if you say we dug up a dinosaur, how do we know that the dinosaur existed like billions of years ago? Well, you just look at how much of the carbon-14 that is left. That should tell you how long it has been around, you know? 2, we use radioactive radiation to monitor thickness of metal sheet. So using beta radiation, you basically control it to make sure that it's not too thin to a point that the beta radiation can pass through. So there will be 2 planes. There will be the machine will have 2 plates. One is the sensor, one is the emitter. The metal sheet is here. So if the metal sheet is too thin, it will penetrate and the sensor will sense it and they'll be like, oh, that's too thin, unable to do that. So the metal sheet has to be thick enough to block the beta radiation. So you might be wondering, why don't they use alpha radiation? Well, because alpha is too big. Like if you use alpha radiation, your metal sheet is gonna be really, really thick, right? And then the third one is agriculture. So agriculture is we use the beta radiation in phosphorus 32, which is an isotope. It determines the rate of absorption of the fertilizer used. So normally we use phosphorus fertilizers for plants. So you can use the radiation in the decay of phosphorus 32, which is present in the fertilizer itself. So you can know how much fertilizer is absorbed. Not the last one. We might use nuclear for defense, and you know about the atomic bomb and stuff like that. And yep, that's basically the chapter. Remember to take your notes, right? Rewatch this video how many times you want. Take your notes. This chapter is quite the important parts are the ionizing and non-ionizing radiation. So you have to understand and differentiate between the alpha, beta, and the gamma rays. Right? Know that. Then you know the application of it. The more important one I would say is the carbon-14 dating and the agriculture one. That's more common questions. And yeah, that's about it actually. You need to remember the structure of an atom, but you do learn that in like Form 2 because chemistry is a part of the Form 2 structure. Anyways, so yep. So I hope you guys enjoyed the video. Leave a like and see you guys in the next one.